Welcome back to Calculus. We're going to do a little bit more involved examples with integration by parts in this video. So if you missed the last one, you might make sure you watch part 1, where we introduced what integration by parts was, and we did 3 pretty basic examples. Now we'll do a little bit more involved ones. So starting here with this arc cosine 2x dx, this may not look like an integration by parts problem. This is not a product, but we don't really have any way of integrating, we haven't yet, the arc trig functions. So integration by parts is yet again our answer for these, as it is with just the natural log function also. So what are we going to do? I mean, we have to pick a u, we have to pick a dv, as we talked about last time. Well, since I don't know how to integrate arc cosine 2x, that's what I'm trying to do. It's going to have to be in the, sorry, I can't read that. It's going to have to be in the u position. And then the dv will have to just be dx. Dx. There we go. So what is the derivative of arc cosine 2x? I might have to look that up, but it's going to be, remember we do have a negative, because it's arc, it's cosine, so it has a negative. Like arc sine, it has a square root. You're going to have a 1 minus the thing being arc cosine squared, and then the numerator is the derivative of the thing being arc cosine, so that's a 2. And always put your dx there. You might need to look back over that. That was 5.6 in our textbook. Not super tough, but it's just a formula you need to know. So is this going to really help us? Let's see. So if we go back, plug in, so we did that part, now we do this part, and usually your UV is your mess, and you kind of dump all the junk here that you really couldn't integrate. So this does become a product. We couldn't do anything with that, but we're hopeful the last leg of the picnic table is going to really help, and it's going to be negative 2x over this. So really I just stuck that x on there. That's 4x squared now. We can change that to a plus. I guess I'll go ahead and do that. I probably could have done that on this original step, but I didn't. Okay, so now this problem. So the beginning part is good, right? It's out of the integral. This is our problem. So just evaluate this problem. How do you integrate this? You might think, oh, it's an arc trig. No, it's not an arc trig because of the x up here. Arc trig usually going to have a constant up top unless this down here is higher than second degree. And we've seen that before. But this is actually a substitution problem because the thing in the denominator is second degree. I mean, it's under a square root. That's okay. The thing under the square root is second degree. The thing up here is first degree. That's a good u-du pairing. Always think big. Think about letting u, and this is a bit confusing because I already used u. I'm okay if you do this, but if you would rather, we could call this like w substitution just to mix it up a little bit so we're not using the same letter for two things. It's okay because it's kind of a new scenario, but I'll just do that. I do need my square, so let's let w be 1 minus 4x squared. dw would be negative 8x dx. Look promising? Looks pretty good, except you might think, I really wanted this to be a 2x, not a negative 8x. Well, you can just multiply both sides by negative 1/4, and you've got it, right? Because that times negative 1/4, not times negative 1/4, is going to be 2x. And so now everything is matching perfectly. Let's go back to our standard black color. So this is now, I'm going to move that minus 1/4 all the way out to the front, if that's okay. And what do I have left over is just 1 over square root of w dw. You know what? I'm going to rewrite that. Again, I'm act like I'm in a hurry here. Let's just take our time. This becomes square root of w, and then the 2x dx became dw, well, 1/4 dw, negative 1/4 dw, so let's put a 1 up there. Okay, now we'll do our cleanup all in one step. Move that 1/4 out front, make this w to the negative 1/2, lots of recopying in these problems. So the integral of w to the negative 1/2 is w to the 1/2. Better put a 2 out front, plus c. And I think we are about done here. Why is that an equal sign there? There should be a minus. Well, that should be a plus if we bring that out front. Oh, let's see here. That should just be minus. Yeah, okay, sorry about that. So this is now our x arc cosine of 2x minus 1/2. And then I could replace w with 1 minus 4x squared and put it back under the square root. And we are going to call that good. We did it. So this is a problem that required integration by parts and then regular substitution, u, or in this case w substitution. And the reason we knew is because we got into this form, which was better than where we were, not great, but that denominator was 1 degree higher than the numerator. There's no other way to simplify it, so it was a good candidate for regular old substitution. Okay, let's do a couple more. This is kind of like one I mentioned at the beginning of class. Let's mix up the colors here a little bit. We'll call this example 5. The beginning of the last video, I think I mentioned integrating x e to the x. And we could do that. If you can do this, you can easily do x e to the x. It's actually one of the easiest ones possible. But I thought I'd mix it up a little bit and go x squared e to the x. This is going to cause us to do something a little bit different. So we have to decide what's our u, what's our du. I don't know if you've gotten the hang of it a little bit yet, but usually you want your u to be something that is easy to take the derivative of, right? Because that's what you do. You want your dv to be something that you can integrate because that's what you do with dv. So that's why ln of x is never dv. That's why arc trig is never dv, because we don't integrate those well without integration by parts. So in this one, it's kind of a tough call. I can integrate and I can take the derivative of x squared and e to the x. No problem. But do you have an idea what might be more convenient? One of the benefits, if you look back to the very first problem we did of letting u be x, is because as you take the derivative of u, its power diminishes. It gets simpler and simpler. And eventually, if you keep taking the derivative of a polynomial, it's going to go to 0. That's not true with trig expressions, right? They just like sine just bounces back and forth from sine to cosine. E to the x does nothing. So I feel more inclined to put x squared here because the derivative is 2x. It's simpler. While e to the x just does nothing. The derivative of e to the x is e to the x. The integral of e to the x is e to the x. So maybe this will help. Let's see. So I set up my first leg of the picnic table, now the top. So x squared e to the x. That's interesting. It's the same thing I started with. It's out front. Minus the integral of 2x e to the x. And usually what happens, every problem we've done so far, is you get here and we can integrate this. This one, we can't. So did we mess up? Do you feel encouraged? Are we in a better position than we were? We are. We're in a better position. So what we need to do is do integration by parts again. So I think if we do it one more time, then it's diminishing. It's going to diminish down to be a constant. So you got to really be, we're going to have a bunch of stuff going on here. Big parentheses, right? Because all of this is going to be subtracted. So we did that. Now we do the top of our picnic table, 2x e to the x minus the integral of the other leg, which is 2 e to the x dx. And I think we can do this. So occasionally you're going to need to use integration by parts more than once. There are times you do it more than twice. We are probably not going to do many of those. So let's distribute this negative through, because this is a really, this could really cause some errors. That becomes a plus. And I could even put the 2 out there if I want. Okay, and now this is very manageable. X squared e to the x minus 2x e to the x plus 2 e to the x plus c. There's our answer. You might notice we could factor an e to the x out of this. And we have x squared minus 2x plus 2. And that is as good as it gets. Nice little problem there. And you might be starting to see, when do I let x be u? When do I let e be u? When do I let ln of x be u? When do I let those be dv? And at the very end, actually, let's do it right now. Let's make a list of, do this in a different color, of what do you want to have as u, what do you want to have as dv. This is kind of a sliding scale. The thing that's always u are the things that we can't integrate without integration by parts, and those would be the natural log of x and arc trig expressions. So we've seen both of those even in this video, I think, or maybe the ln of x was in the last one. But ln of x and arc trig, always u. And then dv, there's not really anybody who loves to be dv, but there are things that just they don't really care, like e to the x, for example. E to the x, it's so easy to integrate. It doesn't matter if it's derivative or integral. We often put that down there. Polynomials, I'm going to put kind of in this part. And we might be tweaking this, but this is just an initial proposal. But polynomials, I like them being u more than often because they get simpler as you take the derivative. They diminish in power, and eventually getting down to a constant where we can, it often means there's not a product. And then the other type that we deal with are trig expressions, and I'm going to slot them in here. These here, I always forget, because there doesn't really seem a real compelling reason to put one in the other, because trig expressions don't get simpler when you take the derivative. They don't necessarily get more complex. Well, I guess the tangents and the secants do. But those you might just have to play around with. But I can tell you, these always are u. Polynomials can go either way, but they probably prefer to be u unless they're matched with an ln of x arc trig. These two, I don't know. They don't. If they're matched up with any up here, of course, they have to be dv. But if they're matched together, which this next one's going to be, it's a little bit harder to figure out what to do. Okay, our final example. How are we doing on time? Trying to time myself now. All right, we're doing okay. We'll keep this under 20 minutes, hopefully. Go back to black. Example 6. E to the x cosine 2x dx. And this one, I don't know if we'll make it under 20 minutes. This one's a bit involved. So here's that example. Who gets u, who gets dv? Well, I'm just going to tell you that it's going to be u. It would take a while to explore both of these scenarios, but it's going to be u that is the cosine. So this order is right. And you might just note to yourself, the problems that we're going to do, if you have an exponential, it's always dv. So exponential is always dv. We put a line like that again. And logs and arc trigs are always u. Okay, with that in mind, this is going to be negative 2 sine 2x dx. And my dv will just be e to the x dx, so v is e to the x. Okay, So doing our picnic table. And a lot of times you're going to do these not really sure this is going to work. Sometimes you just have to try something. E to the x cosine 2x, right? So our setup was there. It was the original problem. The first part's the top of the picnic table, and then the other leg of the picnic table is after the minus and the integral. So we're going to have a minus 2 sine 2x e to the x. And really we feel pretty discouraged by this because we don't know how to integrate that either. In fact, we're worse off than where we started. So whoever figured this out was a really patient person who didn't let themselves get discouraged because we are on the right track. It's just, this is one where we have to do integration by parts again. And so let's do it. So the second integration by parts. You know what, before I do that, this is going to take an extra moment here, but let's simplify this. Just as we don't want to have negatives all over the place, so let's get that, make that a plus. Negatives, excess negatives like that just can really cause us to make a mistake somewhere. Okay, so we're looking at this, and we're going to follow the same rule and say, let's let trig takes the precedent here and gets to be u. This is now going to be 4 cosine 2x. And this is, again, e to the x dx and e to the x. Okay, so we already have this. This is going to start getting really long. And now we're splitting this part. So it's plus. So we've done that, and then that's next. So 2, I'll just be in the same habit of putting the e before the trig, so it looks uniform, minus the integral of this part, which is 4 e to the x cosine 2x dx. Okay, so it looks like this is just a disaster, right? This is horrible. What have we done? We have done integration by parts twice, and look what we have in our integral. And look where we started. It looks like we've gone in a loop. What good have we done? We're back to e to the x times cosine 2x, and we even have a 4 thrown in there. Well, this is actually exactly what we wanted. And again, I didn't think of this, of course, but some really smart person did. Let's just do it this way. What is this equal to? I've been putting all these equal signs over here. Equals, equals, equals. What is it equal to? It equals this, right? So what if I just go ahead and write that down here? Equals integral of e to the x cosine 2x. Just to kind of remind us what we've been doing. And let's get rid of this equal sign so it's not, looks like there's 2 equal signs. So look at that expression on the bottom of the page there. What could you do? This might remind you of an algebra problem. I'm going to write this and then erase it. You know, like, I don't know, x plus y minus 4z equals z. What could you do if you, couldn't you combine, you have some like terms, right? Couldn't you combine those like terms? And that's what we'll be able to do here as well. I can combine those like terms. This is a crazy, crazy move. So let's rewrite the first 2 terms. And now I'm going to add this to the other side. And what do I get? I have 4 of them, and I add it to 1 of them. They're like terms. So now I have the integral of 5 e to the x cosine 2x's. In fact, let's take that 5, if you don't mind, and move it outside the integral. I have 5 of those integral of e to the x cosine 2x dx's. So what was the original problem? The original problem was find out what is that equal to. So look what I can do. I can do old school algebra, divide everything by 5, and I have my answer. I'm gonna move this to the left side. So I actually have figured out the integral of e to the x cosine 2x dx without really ever integrating. It turns out it is, let's see what I can do with this. Let's factor these e to the x's out, if you don't mind, and we'll put it over the 5. So I'll have e to the x over 5 times cosine 2x plus 2 sine 2x. And we got it. Is there a plus c on this? That is a good question that we never really integrated. That I'm not sure the answer. I'm going to have to look into that, and maybe you can ask me in a chat session sometime. But I'm going to leave it like that for now. So we've done it. We have the integral of